How you going, Veritas? Just watching your video, Objections to the Kalam Examined 1, and wanted to again take you up on the second law of thermodynamics area. You say that you can apply the second law of thermodynamics to the universe. Now, I assume you're talking about, I'm not sure whether you're talking about an infinite universe or a finite universe. Just to clarify what I believe, well, I suppose, that based on all the evidence and things of that nature, that physical scientific evidence, that is, that the universe is infinite and beginningless, infinite in time and space. Now, so if you're talking about that kind of universe, then you can't apply the second law of thermodynamics to that simply because it is infinite, and infinity doesn't have a boundary, and it's the boundary which is required in order to use the second law of thermodynamics. The system must be closed or isolated. It must have a boundary, and an infinite system does not have a boundary, so you can't use it to describe that. Also, if you're talking about the Big Bang cosmological universe, where the universe itself is finite size and expanding, then you also can't apply the second law of thermodynamics in that case either. And the reason stems from the entropy and the changes in entropy that the second law of thermodynamics describes. Now, entropy is a measure of the ordered states, the states of a system. Now, if the system you're talking about is the universe, then it's where all the particles are in the universe, what states all the particles are in the universe. Now, the certain number of those states, it could be in the universe, could be in one of a ridiculously big number of states. To take a simpler example to explain entropy, which is not an easy concept to get your head around. Granted, it's not at all an easy concept to get your head around. Neither is most of thermodynamics compared to most of the other classical physics anyway. So, entropy you can look at from a state point of view. So say your system, this is a good example, your system is a packet of 52 playing cards. Now that system can be in any one of lots and lots of states. 52 cards, so it can be 52 factorial states, 52 ways to order all the cards. Now, how easy it is for us to understand, for us to know the order of the cards is the measure of the entropy. It's a probabilistic thing. In its most pure definition, entropy is a probabilistic equation. It's a very simple one too, which is why you get simple analogies with the cards, like I'm about to continue with. Anyway, yeah. If it's a factory ordered pack and we know exactly where everything is, then the entropy is 0, because we know everything about it straight away. If it was cut just once, and then, well, we would have to know that where that cut was. That would take some knowing, some effort, some questions we would have to ask. But not very many, as long as we found that one cut, we would know. But if someone then shuffles the deck, we'd have to ask a lot more questions to find out the exact configuration of the deck. Now that is the clearest way to portray entropy. Entropy is that difference between just the pack being cut once from a state that we understand, from we know, and then being shuffled. So it's the number of states and how ordered they are is what entropy describes, is what I'm trying to get at here. Now, your universe, the Big Bang cosmological universe, which you're defending sort of here, is an expanding universe. Now, the problem with applying the second law of thermodynamics to an expanding universe is that as it expands, more states become available for the universe to be in. As more states become available, then it'd be like trying to play the game of figuring out how the cards are ordered when I was constantly throwing in new cards. You know, it's impossible. You don't know, you know, unless you knew what cards were being thrown in. So if you have your expanding universe, you're constantly adding new states, and you can't use the second law of thermodynamics to describe that either. Your number of states needs to be constant, and this is what's usually encapsulated in a closed system. Your number of states in a closed system is constant. In an open system, your number of states is not constant at all, because things could be changing, and that's the reason why you can't apply the second law of thermodynamics to an open system, is you need a constant number of states. And so, in an infinite universe, you definitely don't have a constant number of states, you have an infinite number of states. And in an expanding Big Bang cosmological universe, again, you don't have a constant number of states. So you can't call that system thermodynamically closed. Sorry that was a bit long-winded. It's a difficult thing to explain, but I'll just continue watching your video, and I hope you can hear me a lot better actually with this. So I'll get back to watching.